Hello, everyone. This is Professor Ma, and this is the introductions on the sections for divergent theorem. We start out the setting is a three-dimensional flow. We have a 3D vector space. Think of it as a three-dimensional flow. Okay, and the divergence, it's these functions we make, we forms. Take the I components, take the partial respect to x, take the j components of the vector field, take the partial respect to y, and then take the k component, take the partial respect to z. And when you finish it up, you get some sort of functions. It's sort of I shouldn't call it f because I'm going to call it diff f. It's some function x, y, z. And that function is called a divergence of the vector field. So from the vector field, a three-component from vector field is you get this one single functions. And what's good for? Well, we can calculate the flux with it. So this is the condition. So suppose we have a solid, and the solid, of course, is enclosed by a surface, and we're going to have we're going to define the outward normal. Okay, and we're going to call that the normal vector. We're going to call that U. So the things I have to in mind, maybe easiest is just take a ball and think of on the surface we have this outward normal vector N defined at each location. Okay. There are different ways to do this outward normal. The way I'm drawing it is if this is x, y, z, I'm doing it in the z regular. But in other cases, you might want to cut the two surfaces into these forms. And so then to compute our normals with these two surfaces. That comes in later when we set up what divergence theorem is going to tell us. And, okay, we want to compute the flow. Okay, so we have a flow F, okay, in different direction at different point. So these are capital F, and we want to calculate the amount of total flow across the surface. The surface, of course, is this sigma. So we want to calculate the surface over here is the surface of the sphere. Okay, and then in that case, the divergence theorem says, oh, you can actually take the triple integral over the regions, over the entire sphere, a triple integral of the diverging functions. So this is one of those functions that converts surface integral and converse integrals back and forth between each others. Since the normal we define over here is pointing outward, so we'll call this the outward flux across the surface, sigma. In these calculations, it says, now we can do a triple integral. Why? But sometimes it's easier to do the triple, to convert the problem into a triple integral. Okay. So let's do some examples. So let's calculate the divergence. Okay. So here is the flow vector field for the representing the flow, and this is the sphere, the surface of the sphere. We want to compute the outward normal, outward flow, flux, if you like. So the divergence, so I take the x component part with respect to x, y component, j component y with respect to y, and the k component z with respect to z. So I get 1 plus 1 plus 1. That's 3. So the outward flow okay, is going to be equal to 3 is an integrand over the entire sphere. And that the integral over the entire sphere is the volume of the sphere. So therefore, I get 3 times the volume of the sphere, and that is the total outward flow. Okay. And here's another example. This time we find the outward flux, okay, over the cylinder. So we'll calculate the flow across the cylinder. So this is x squared plus y squared equal to 1. And we'll have f of x, y. This is the flow vectors. So calculate the divergence. Okay. Oh, by the way, when I say flow across, that picture actually, I mean flow across in all directions. It seems so. It actually, if I want to calculate the surface integral, I got different pieces of surface. It's complicated to integrate. But for these, using the divergence theorem, says, I just integrate this over the cylinder. Okay, and that we can convert that into cylindrical coordinate, x squared plus y squared. Every time we see that, that's r squared, so automatically we think of that. So this is r squared plus 1. And then dv is rd theta, or dz also, since z components, it stays as z. And so the integrand of this part is r squared, and this is the differential conversions, and that you can integrate it out. And so that's divergence theorems. Okay, and that's it. Bye-bye.